Welcome everyone to another excellent adventure, a new lecture, CS 340. I'm your host, Frank. It's co-host Payman. He's going to stay awake and be involved the entire lecture, I'm sure, showing me his shiny, happy, smiling face, giving me the energy to keep going despite fall. Today is actually going to be pretty simple lecture, basically setting up some intuition in geometrical understanding of what's going on, principal component analysis. And then on Friday, we'll talk about the maths of principal component analysis. But just to remind you, last time we talked about maximum a posteriori estimation, where we showed the maximum a posteriori estimation maximizes the posterior probability being proportional to the likelihood times the prior, the likelihood being sort of standard loss that we've been looking at, the unregularized loss, the prior being our prior belief about parameter values. The likelihood measures the probability of, the data given the parameters, and the prior measures the probability of the parameters before we see data. If we make an assumption about IID training data, and make an independent assumption about the dimensions of our parameters, i.e. independent and identically distributed assumption about the individual parameters. That's equivalent to writing a loss function. Map estimation is equivalent to writing a loss function, which is the sum over the log likelihoods and the sum over the log priors over the dimensions. The log likelihood is an error function, the log prior is a regularizer. If you use squared error, or if you use a Gaussian likelihood, you get squared error. If you use a Gaussian prior, you get L2 regularization. And we talked about a bunch of different forms for that and tied it into a bunch of the earlier work that we did. Cool. Today, though, I said we're going to start talking about part 4. And there's no better place to start than to remind you about the difference between the way machines see things and the way we see things, right? So when I give Payman a rectangular or a square, maybe 28 by 28 pixel grayscale matrix, and I say, hey, Payman, take a look at this matrix, he says, oh, I see a 3, right? When a computer sees this 28 by 28 matrix, it's just some grayscale values, right? Okay, these happen to be permuted rows and columns but the point is that the computer doesn't look at this and recognize it as a 3. A computer sees a bunch of grayscale values in this 784 dimensional space, something like that. But maybe actually, if we want the computer to understand what's in this, random matrix of grayscale values, maybe we shouldn't, just make it treat it like a combination of pixels, right? Maybe we want to learn a better representation. We've talked about this a bunch. We want better features. So how do we learn better features for whatever downstream task? Okay. And to get there, let's think about what is one of these high dimensional objects, right? So we can look at this 28 by 28 images as, for instance, a weighted sum of 786, is that right? Yeah. 784 individual pixels, black pixels, right? So we have 784 images. They're just black pixels in each of the locations. 1, 2, 3, okay, but that part we skipped away from those and we said, okay, here's a pixel value, it corresponds to this. Here's a pixel value, it corresponds to this, right? And the weights that are associated with these, later on today, these are going to be Zs, and these are going to be Ws, something like that, okay? So basically you have 784 single pixel images, and you can write to this 3 as a weighted combination of those images. Make sense? Yeah. And basically the weights basically say how much is this pixel turned on in this image, or how much of it in there. Weight is 0, so it's turned off, so it's white. Weight of 1 means it's black. So I think you could argue that this is a relatively non-intuitive basis, right, for what an image looks like. And just to throw it out there, just for the fun of it, right? If you unrolled this into a 784 dimensional space, right, then you could actually take this W and this W and think of them as vectors. You know, there's a one in this location, and then there's another pixel location, there's a one in that location, and there's another, and basically you have a 784 dimensional space, right? And this 3 is in the 740 dimensional space, and it's like a weighted vector in that 740 dimension, not 784 dimensional space, right?
Each pixel is a basis vector for a pseudo vector space.
So each pixel is a basis vector. I don't know what pseudo vector space means, but it's a basis vector in a 784 dimensional space. Literally, it's just a one column of the 740 dimensional space. And if that means it's a pseudo vector space, great. It's just a vector space for me. Yeah. So that's not ideal, right? What we'd really like is we'd like to have a lower dimensional space. So the weight denotes the intensity of the pixel. Yes, indeed. Yeah. So this is not really what we want, right? We want a lower. We know that we want a lower dimensional representation for all of the supervised learning reasons that we talked about before, right? It's also kind of non-intuitive. We'd really like to think of the 3 as being made up of a digit as being made up of a small number of parts, right? Fine. So, you know, if this is some part W1, this is some part W2, and this is some weight to Z, you know, I1 or whatever, and ZI2. I'd really like to be able to make a 3 by, you know, having some digital alarm clock if we do unroll it and fit some model, would we be able to recognize this? Yeah, so yeah. No, so that's exactly the point, right? So like we're gonna have we'll get there, but we're gonna have the coupon collecting problem if we, you know, that like distances are really big in the 784 dimensional space. Coupon, you know, if we want to count inside regions of this and like do classification, it's really hard. We need a really, really big tree in order to fit it, and we need huge amounts of data. So what we really want is we want a lower dimensional representation that's made up of intuitive parts, right? So in a digital alarm clock, if you turn this one on and this one on and this one on and this one on and this one on, then you've got a 3, right? And that's basically what we're showing here. So we're saying, okay, well, you know, what if now what if we have a 1, 2, 3, 4, 5 dimensional space, right? And we have 5 axes, and these axes, that's the worst. I don't know how to do five dimensions. I guess I could draw 3 dimensions and then 4 dimensions and then, you know, 5 dimensions. You get the idea, right? Yeah, so I mean, just note though that these dimensions in this 5-dimensional space are linear combinations of these original dimensions. Okay, that's actually going to be relatively important. Okay, so if we actually did the digital alarm clock thing and we had 7, that is, I'm tired. I'm very tired. We had 7 different parts, right? So we'd have W1, W2, up to W7. And then there are weights associated to each of those, right? We can build 3s by turning on bits. Why some of pixels are not in 0 or 1 instead of 0.6? What?
Well, I think it means why it's not binary, it's grayscale. We were dealing with grayscale values, right?
I was going to say there's 2 questions, right? One could be like, why are there grayscale values here? Well, that's a choice we made, right? And another question could be, why in these examples are we making it so that these are just 0s and 1s for the weights? That's largely the latter is largely pedagogical. The former is, you know, fairly important to, like, you know, low resolution images. So anyway, so we can represent these high dimensional objects with a pretty small number of values. So these are 784 dimensional, right? These live in that way, in R to the 784. And here, if we had these parts and we can only do, 0, 1, then this is, in 0, 1 to the 7, right? Cool. More generally, these are going to be real valued at some point, so it will be R7. So we're reducing dimensionality. It means our estimation problem. Like, so basically we can replace the x's by the weights of different parts. We got the 784 dimensional x. We replace it with 7 numbers, and this should make learning easier, right? But the question is, like, where do these parts come from? And where do these weights come from? Okay, fine. And that's basically what we're going to talk about in part 4. We're going to do linear models for unsupervised learning, and basically they're going to be latent factor models in a number of different ways. Okay. So the part weights, these are going to be the weight. Whoa, hello. These are going to be the weights. I'll also call them loadings. It's hard for me to. Okay. I think weights is a little bit confusing because we talk about weights and parameters in other parts of the class. These are definitely different. These are the basis, new bases. You can also call these the basis. That's probably actually better. We should just call these the basis. That's not right, because the other one is the basis. Anyway, we'll call these weights. These are the weights for the basis. But it can be hard to find a good basis, right? And this part of the course is about learning such a basis from data. Okay, so we're going to have some data matrix X as always. Note that there is no Y here. Okay, all we have is our data matrix X, and we're going to shove it through this blue box or black box latent factor model, and we're going to get out Z. And why do we want such a thing? Well, if we then use this in a downstream supervised learning task, we could use the part weights as our features. And we already know that that's a good idea to load to use features that are well aligned or are lower dimension, because you tend to overfit less if the features are still task related. You can use it to do outlier detection. If you have parts and you can't construct a new object from those parts, then it's probably an outlier in some sense. So that's a nice way to do outlier detection. The previous example, we took a 786 dimensional real valued vector and compressed it into a 7-dimensional binary vector. That's good for compression, so on and so forth. Visualization. If you take a very high dimensional vector space and you compress it down or reduce it into a 2-dimensional basis, you can then visualize it by actually directly scatter plotting the data. And we can use it to interpret the data that we have, our high dimensional data, because we can try to figure out what the parts mean and that sort of thing. Okay.
Is it like clustering on the data?
Great. Lovely, Ramon. I appreciate it. And the first thing that we saw that was like this was unsupervised learning, i.e. part 2 of the course, where we looked at, for instance, vector quantization that came out of k-means. So let's remember what we did when we did k-means for vector quantization. We're going to turn this into some notation that then we're going to turn into intuition about what we're going to talk about as principal components analysis, which will be our first linear latent factor model. So when we did k-means for vector quantization, we ran k-means to get a bunch of cluster centers for C in 1 to k. And we got a cluster identity, a label for each object I in an unsupervised way, right? So this would be 2, and this would be given, y hat, 1 equals 1, whatever, y hat 17 equals 2, okay, whatever. Okay. And we said, when we do VQ, we replace the actual feature value of this point, for instance, with just this, with you know, so if this is x13, right, we replace it with w3. Okay, we say that these are basically the same. So we summarize every one of these points with its mean, right? And we can sort of think of this as a really bad latent factor model, okay? So to sort of start to build a little bit of notation, if we think about vector quantization in latent factor modeling kind of terminology, if the original data space was three-dimensional, we could write xi trivially by having three basis vectors and weights associated with them, okay? This is like the one pixelon representation of images. It's a pointless latent factor model because we just have that the latent factors are the weightings, right, are just the values themselves. But if x is in cluster 2, for instance, xi is in cluster 2, vector quantization approximates xi by the mean of cluster 2 w2, right? And the way to think about that is that we have, you know, that's exactly what we have. We have some weights. These are the z's again, right? And we have the cluster means, and those are going to be the parts. Okay, so these are the parts, and these are the weights. Okay, and the parts are the means from k-means. And the funny thing about vector quantization is that it did in vector quantization, like in the case that we just did, said that the weights are, you know, 0, 1. And in fact, it's a one hot vector, right? Okay. So vector quantization, we can view it as a latent factor model, right? So we stick in x, we do some sort of vector quantization operation, we get parts out, these are the cluster means, and we get these weights, which are one hot vectors, which are the assignment of clusters, of data items to the clusters, right? And now we know that, like, when and if we're doing supervised learning, and we're trying to cluster the data, and we're trying to assign labels, right? And that we assume that the colors are the true labels, right? Classification would be super easy in this representation. Not so easy in this representation, but super easy in this representation, because literally the weights for the parts are exactly in correspondence with the class labels, right? So VQ is just using one part, so it's basically memorizing k points in x space, but what we want is a combination of parts. And what we're going to talk about intuitively today, and then we'll do the maths on Friday, is principal components analysis, which is a generalization that allows continuous weights. So in other words, these are not going to be in 0, 1, but these are all going to be in R now. Okay, so you can have more than one non-zero positive weight. You can use fractional weights and even negative weights. So like having a negative part is a little bit weird, but that's one of the things that we do in PCA. Principal component analysis has been around for a long time. It's been invented in many different fields. Yeah, you can Google it, you can Wikipedia it, and I recommend that you do in preparation for Friday. We're gonna have to introduce some notation, and I recommend that when I'm done expanding this slide out, you screenshot it and put it in a window on the side or something like that, because it can be just a little annoying and confusing, although I've done a little better job in this section than I did in the last one in terms of not getting it screwed up so far. This is the only lecture in which, when I lecture on this, I actually keep the notation around somewhere so I can remember. I wrote it on the board over here, which you all can't see, but I have a big whiteboard, and I just make sure that I have the Z's and the W's up there, and if I look over there, you'll know why I'm looking over there. It's not some emotional difficulty. So anyway, remember we're going to be modeling some data matrix X as always, and X is in by D. Okay, so we're going to take in this matrix X and K. So we're going to have some function PCA which takes in X and K, and then outputs Z and W. And these two matrices look like this. Z is going to be K by N, and W is D by K. And the individual vectors that make up those matrices are given here. So for every row of W, we use the notation WC. Okay, each WC is a part. It's also called a factor or a principal component. Okay, cool. And just to be for every row of Z, we use the notation Zi. And every Zi is a set of part weights or factor loadings or features. Okay, and for the columns of W, we use the notation that we used before, which is W sup J, and that's index J of all the K parts. Okay, fine.
Cool. Is definition of factor loading same as the definition here?
Okay, great. So I've read the definition of factor loadings from other source that is a correlation between PCs and original variables is the same as the definition here in the Z matrix, the PCA coefficient matrix. Okay, so this is why we're like doing this. There's a lot of different terminology for PCA, like annoyingly a lot, like annoying, super annoyingly a lot. Okay, so and sometimes actually in the statistics literature, we use different symbols for different things. So let's just go with the symbols here and just like, this is what we're going to say. Okay, so the W's here are the components. They're actually, these are going to be the bases, and Z's are going to be the weights that we apply to those bases. Okay, and we're going to use features. I'll try to use for the remainder. I'll really try to use features or part weights to refer to the Z's for the remainder of the lecture, just to try to keep things as clear as possible here. But the reason why we use that terminology here is that we're thinking about using these as features for some ongoing, for some later supervised learning task, right? And the principal components, these really are, the axes, okay? So using this notation and terminology, we can write our approximation of one entry in our data matrix, row I, column J of X, as a sum over an appropriate weight, weights applied to basis elements, as you would expect. I think it's actually easier to look at what's going on here, right? So what we're saying is, we are going to construct. Actually, I think this is the easiest way. We're going to construct a particular entry by taking the inner product between W column J and Z row I. Okay. At the end of the day, that's what's happening. Okay. And in K-means, you take the index J of the closest mean. In PCA, Z gives you the weights for index J of all means. Okay, so there's a lot of ways to write the approximation of the vector. This is honestly my favorite way. The entire vector xi, which is d by one dimensional, is just going to be our basis vectors, our times the feature weights, or the weights. Okay, so this is d by k. So these are going to be k different sort of axes, or we'll get some examples of this later. And then the relative position along those axes for all k. That makes up the data item xi, x hat I. Okay. Fine. So PCA approximates each entry of the data matrix by an inner product. Okay. PCA approximates each row of a data matrix by a matrix vector product. That makes more sense. These are the weights. These are all of the axes, and that gives you sort of where you are in space by just weighting up those axes. And in the notation that we use, PCA approximates the matrix X directly by using the matrix, using the notation that we have here, directly by the matrix product ZW. Okay, so this is just getting all the transposes and all this sort of stuff right. The fundamental thing that you need to think is really each data item is the weighted combination of a bunch of basis vectors. Okay, and that's what this is doing. Okay, you can do all of the data items at once by weighting all of the basis vectors for all the instances simultaneously. Okay. So PCA is also what is called a matrix factorization model. And it should be pretty clear what's going on here. Like X is the thing that we have. Z and W's are the unknowns. So I'm going to hand you an X and you have to, and a K, and you're going to tell me Z and W. And you should be very well aware right off the bat that this is an under-constrained problem, right? Obviously, we've got, who knows what the Zs and Ws will be. PCA is going to be a particular mathematical choice of which version of this, which of the possible ZW decompositions of X is the one that we're interested in. Okay. So the critical part is that if you have a magic piece of code or piece of mathematics to give you such a matrix factorization, then you can look at PCA in particular as a change of basis from X to Z. So X is an original d-dimensional data object, feature vector, whatever you want to call it. And Z is now a k-dimensional vector, and we're going to generally look for k less than d. And to answer Ramon, is the closest to the approximation determined by the size of k? Yes, right. If k is very, very small, then it's unlikely that n times k. If n times k plus k times w is smaller than n times d, then there will be an approximation error. If that sum gets greater than n by d, then you have an overdetermined, you have more parameters, so you can overfit and you can basically perfectly reproduce X. So yeah, K is gonna, yeah. Cool. Okay, yeah. Awesome. Hopefully this is making a little bit of sense. Okay. So there's some applications of PCA, and again, you really could be thinking of this as like, this is just setting up linear latent factor models and matrix matrix factorization methods. Here we have X, whatever our data matrix is, we can replace X with a lower dimensional Z, right? And if K is much smaller than D, then this is going to compress the data. And often this results in a better approximation than vector quantization. So just to give you a really trivial kind of silly example, if we have this data matrix X, right, kind of a silly data matrix, but we know that we can make it exactly equal to Z times W. And the critical part is that the original X is 64 elements. And with this particular choice of Z and W, then with 16 elements, you can predict all of X with perfect precision and many fewer parameters. Okay. This works in higher dimensional spaces. So here's another data matrix X. You can decompose this into the product of Z and W. So the original matrix is 500 by 501, Z is 500 by 100, and W is 100 by 50. It's 100 by 501, excuse me. What am I saying? If you fit this matrix factorization method, again, we'll say it's PCA, that's fine. the original image has 250K images. This has around 100K numbers. And when you take the product of this matrix Z with this matrix W, the matrix product is, basically visually identical for all intents and purposes, right? So that's fairly compelling, right? And again, I couldn't get this in between class to go. Basically, as you increase the number of dimensions, as you increase the number of K, this approximation gets tighter and tighter. Fine. We talked about another application for latent factor models, like outlier detection, right? So again, we have this magic PCA thing, and let's imagine that it gives us parts like this and weights like this. If you then got a new image and tried to fit the weights such that you tried to build this image from these parts, failing to do that would suggest that, say, for instance, this image is an outlier with respect to wherever you train, whatever images you use to train this basis, right? Okay. Fine. So another thing that you can do, and this is like hinting at downstream tasks, right? You can do what's known as partial least squares, which is you basically use PCA features as a basis for a linear model. So you compute some approximation to your data matrix X as in ZW using this magic PCA routine. And then you use the Zs as features in some theoretically lower dimensional linear model where now you have a K dimensional feature vector rather than a D dimensional feature vector. And this is now a standard change of basis like we talked about. And then we talked about visualization. Again, if you have this magic PCA or linear latent factor model, like if you can project your data onto some principal components where these are the weights, and this is, for instance, principal component 1, this is principal component 2, you can take very high dimensional data. This is super useful. You can take very high dimensional data, project it down into lower dimensions, and potentially see cluster structures emerge directly, right? So this is one of the ways that we looked at the data. This is actually the tools that we used to look at the data the high dimensional data that we looked at earlier in the course. And you can augment this with other visualizations and whatever. Okay. We can ask where do these components have an interpretation visually? Okay, so great. So we talked about the last application of linear latent factor models is sort of in unsupervised discovery about your data, which is to say you can like run PCA or some other latent factor model and try to interpret the dimensions. This is actually kind of fun to read about, right? You take a bunch of people and give them a survey, and you take their multiple choice questions, responses, or so on and so forth, and then you try to find the 5 principal axes of variation. You do a latent factor model of this, and then you interpret the axes of X is their responses, right? And then we have ZW, right? And Z are going to be the loadings, and these are going to be the principal personality axes of the respondents in such a survey. And you can go back and then look at the data and the people that are projected onto these axes and the weights that are assigned to them. You can interpret the axes like openness, conscientiousness, extroversion, neuroticism, these sorts of things. I sort of feel like I'm like maximally on all of these. I don't know. So, okay, maybe not agreeableness. Okay. Anyway, that was a joke. No laugh payment, really? Come on. All right. I'm trying. I'm really trying. I'm trying. This is tough. Okay. So what's PCA or linear latent factor models? What are they doing? In particular, what is PCA going to do, and when should PCA work well? We'll talk about geometry today, and then we'll do mathematical implementation next time. Okay. So Doom. Yeah, it's, we all fail sometimes. Oh, jeez. Oh, it's, this is a, it's COVID. It's, we're in a new lockdown phase. It's challenging. I'm talking into a screen of doom with Flux on. Yeah, well, I think Monty's lovely, but I strongly dislike COVID. Anyway, we all fail sometimes. I can just see Akim's teaching review. It's okay, we all fail sometimes. That's going to show up in like my promotion case at UBC. It's great. It's like it's awesome. Anyway, so Doom, yeah. Well, when we played Doom, like there's multiple levels. You go in here, you can come up here. You're up in 3 space. You can go on the roof, and you can come down and shoot this guy, or shoot him with a chainsaw or whatever. That's good. I'll try to remember that, Alan. I'll put it on the final. We all fail sometimes. That's great. Okay, so you're playing Doom. You're moving around to 3 dimensions, and you have this like 2D projection thing that that is the overhead map feature, and that's kind of like, that's actually a latent factor model of player location. So if you can describe the actual player location at time I by 3 coordinates, that's the X, Y, and Z, like where you are on the map, and height as well. The overhead map approximates these 3 coordinates with only 2, right? So the Z is just the X and Y coordinate, and the latent factors are just like so. They're 1, 0, 0, and 0, 1, 0. Okay. So the approximation xi of the overhead map in Doom, again, you take this thing, you transpose, and you get this. You take this thing, you transpose, and you get this. That's where the notation is just a little bit dicey and easier to look at on your own, actually, right? So xi is approximately the weighting of these 2 basis vectors, right? So if we're ignoring the 3rd dimension entirely, okay, fine. That's, yeah, the overhead map ignores the height. So we've got, your Doom positions in X, Y, and Z space. You've got the XY plane, and you just project down onto that plane, and that's what's going on. And this is not a bad assumption if the world is flat, so on and so forth. It's a poor approximation if the heights are different, in particular, if you choose just the XY plane, right? And the idea here is there are these, I'm sure you've seen, thanks to David Attenborough and other naturalists or nature commentators or whatever, these crazy goats that go up and lick dams to get salt, right? Okay. So project to the plane, maybe not a good idea, but if somehow we could find the coordinate system of this plane, we could explain, that's okay, yeah, fair, fine. If we can find the coordinate axis of the dam, then we could describe the location of these goats with very high accuracy. The dam is slightly curved, so it's not absolutely perfect, right? We could describe their location very, very well relative to one another by finding these basis vectors, and then the relative weight of each of these basis vectors to describe every goat position. Yeah, fine. Okay. So a better K = 2 approximation of 3 space is to find the basis that spans where the players actually are, and here the players are the goats, and it's not so much a single player, multiplayer, the first person shooter. Yeah. So let's think about what PCA in particular with 2-dimensional original features and 1-dimensional latent space looks like. Okay. First, we're going to contrast what's going on with least squares. So in least squares, we try to minimize the vertical squared distance. We only care about predicting the yi's, right? In PCA, note that we do not have a yi here, right? We only have the x's, right? And what we want to do, you can think of it as we're predicting features, but really what we want to do is we want to find a vector and then minimize the projected distance of all data points onto that vector. Okay. So note these are this way, these are towards the vector. Okay. orthogonal to the vector. So PCA is going to find the line W, right? Or the more to the point, the basis vector W, right? That minimizes the square distance in both dimensions simultaneously. Okay, cool. When we get into the nitty gritty, what you're going to see is that basically W, we're going to constrain W to be unit length and orthogonal, and we're going to constrain W to basically be a rotation, right? So you can think of W as being a rotation and then a projection, and then the weights are a projection onto that rotated basis. Okay, so the Zs, the weights that are assigned to individual data items, are positions along the projected line. Okay, cool. And this means that, you know, interpretation of the axes of a PCA projection are possible. And generally speaking, what's going to be the case, what's going to be true is that the axes are going to be linear combinations of the original features. So if we have, for instance, data, which is the height and weight of children, right, two-dimensional, and we do some sort of PCA projection with k = 1, so one basis vector, one principal component, then we find the direction that minimizes these squared errors, right? Or these errors, right? And then the interpretation of the latent factor would be some measure of size, some linear combination of height and weight, which is like a generalized size in some sense. If our original data space is three-dimensional and we do a one-dimensional PCA, we find the line minimizing the square distances. With PCA, k = 2, we find a plane that minimizes the square distances. So here we have three-dimensional data. Then we find our, you know, W2 and our W1, and then we have loadings. Sorry, we have features or weights for every data item that situates them, projecting them onto the plane in all instances, and gives you the coordinates in a lower dimensional surface. Cool. So that's it for today. We're going to do the particulars and the maths on Friday. So latent factor models try to learn a basis Z from training examples X. Okay, so no, there's no Y. Okay. Usually the Zs are some sort of part weights for parts WC, right? It's useful for a bunch of stuff: dimensionality reduction, visualization, factor discovery, so on and so forth. Principal components analysis, which we just started talking about, or principal component analysis, excuse me, basically rewrites every training example as a linear combination of parts, where we treat the data matrix as a matrix to be factorized into a product between features and parts, and features Z and parts W. We can think of W as some best k-dimensional k-dimensional hyperplane, and we can use Z as the coordinates in this lower dimensional space. And it's actually not that hard to code up and to use, so we'll talk about how to code it up next time, and the maths on Friday. Questions? Thank you. People are running away. It's Monday, yeah. Yeah, Wednesday's chill. Looking forward to it. Enjoy the holiday, everyone. Okay, simple lecture, simple time. Thanks, Pam. Lovely to see you.
Cool. Thank you. See you Friday.
Cheers, everyone.